In the previous section, we considered fundamental probability ideas. Here, we'll extend this by using probability to understand how different events are related. I'll begin by reviewing the ideas of independent versus dependent events. Then I'll introduce the idea of conditional probability and work through some conditional probability calculations. Let A and B represent two random events. Then A and B are independent if knowing whether or not A occurs does not give us any new information about how likely B is to occur. Otherwise, A and B are dependent. Consider the example of a coin toss. Suppose I toss the coin twice. Here, I can think of the first toss as the event A and the second toss as the event B. Whether or not the first toss is a head doesn't affect whether or not the second toss is a head, so these events are independent. Now let's look at an example of dependent events. Suppose I have a fun pack of Skittles, which contains 4 each of 5 different colors of Skittles. I like to eat my Skittles by pouring them out one at a time. I can think of the color of each Skittle as I pour it out as a separate event. If the first Skittle is red, this lowers the probability that the second Skittle is red, because there are fewer red Skittles remaining in the package. That is, the color of consecutive Skittles are dependent events. We can formalize the relationship between dependent events using conditional probability. The conditional probability of an event is its probability after some new information is taken into account. Here's some notation we'll use to represent this. Recall that P of A is the probability that A occurs. The conditional probability, written A given B, is the probability that A occurs given that B occurs. Here, I've applied this notation to the Skittles example. Since there are a total of 20 Skittles and 4 of them are red, the probability that the first Skittle is red is just 4 out of 20. But the probability that the second Skittle is red depends on the color of the first, so here I use conditional probability. If the first Skittle is also red, then there are 19 total Skittles and 3 red Skittles remaining, so the probability that the second Skittle is red is 3 out of 19. But if the first Skittle is a different color, say yellow, the probability that the second Skittle is red is 4 out of 19. Why are we looking at this idea? We can use it to help us understand and answer the following kinds of questions. Are bicycle helmets effective? That is, does wearing a helmet make a difference when a person gets in an accident? A water well is contaminated with methane. What is the probability that the contamination is a result of fracking as opposed to contamination from other sources, for example, naturally occurring methane? What are the risk factors for developing severe symptoms from a coronavirus infection? Each of these questions asks how the probability of an event is affected by some additional information, and thus can be addressed using conditional probability. Let's take a look at some data related to the bike helmet question. This data is taken from a 1996 study in Seattle, Washington. The individuals for the data are cyclists who were involved in an accident while biking. The researchers checked 2 variables, whether or not the cyclist was wearing a helmet and whether or not the cyclist suffered a head injury. Based on this information, we can compute how the head injury rates for those wearing helmets and those not wearing helmets compare. That is, we want to compute the probability of a head injury given that you're wearing a helmet. A total of 1,729 individuals were wearing a helmet, and of those, 225 suffered a head injury. So this gives us a probability of 225 over 1,729, which comes out to be 0.13. That is, a person wearing a helmet has a 13% chance of suffering a head injury. Now we compare this to the probability of a head injury given that you're not wearing a helmet. A total of 1,661 individuals were not wearing a helmet, and of those, 532 suffered a head injury. This comes out to be 0.32. That is, a person not wearing a helmet has a 32% chance of suffering a head injury. We can see that wearing a helmet seems to be associated with a much lower risk of a head injury, suggesting that this is a useful safety measure. Let's look at this data a little more. When working with conditional probabilities, it's key to understand what information we already know. This often corresponds to understanding the denominator in a probability calculation. Here I've computed 3 different probabilities to highlight this. The first is the probability of a head injury without any additional information. This is in reference to the entire set of 3,390 cyclists studied. So this is the denominator. Of those, 756 experienced a head injury. Overall, we get a head injury rate of 22% among this group. The second probability we calculated on the previous page. The final calculation shows the probability of wearing a helmet if you had a head injury. This is switching what we know and what is being sought in comparison to the previous calculation. Whereas the second probability first assumes that an individual is wearing a helmet and thus used 1,729 as the denominator. The third calculation first assumes that an individual has a head injury, and this uses 756 as the denominator. If we want to understand the effects of helmets on head injuries, the second probability most effectively helps us do this.